This is Team 43 of the space with our preliminary design report presentation.
Okay, so for the descent and lander system, our goal was to place a detector more than 5 centimeters, meaning like under the topsoil of the Martian ground. So in order to do this, we designed a cone that will be dropped from the deployment hatch, and it won't slow down at all because we want it to speed up and just lodge itself into the ground. So in order to do this, the cone itself is going to be like a plastic. Next slide. Yeah, so the shell itself is going to be plastic. It's going to be 3 millimeters, so it's going to be strong. And we guarantee that it's not going to like flip or do anything once it exits the deployment system by like putting the center of mass close to the bottom of the tip of the cone, so that if it were to have any angular momentum, then it would just correct itself on its way down. As for the actual payload system, the 2 parts I just described, the first part, the outer shell, the second part is the detector and the communicator bit. So the idea is to have a detector at the bottom of the cone that gets entered into the soil. And if there's water in the soil, then the circuit will complete, and then there's going to be an increase in the, or there's going to be a voltage, and then the communicator will be able to be activated.
There have been numerous studies on Mars that point towards the existence of water. And more recently, the existence of water in recurring slope lineae, as the water in the soil causes the dark coloration that is a signature to RSL. Studies have generated a sort of model for these RSL where there is some sort of aquifer about 50 centimeters below the Martian topsoil, and this aquifer is generally either ice or extremely briny water. And then in between that aquifer and about 2 to 3 centimeters of topsoil is some moist soil containing water and hydrated salts. And so our experiment then is to deliver our payload underneath those first 2 or 3 centimeters of dry, waterless topsoil and into that moist soil with this briny water mixture. With our water sensor probe, we can then detect for the presence of some sort of conductive medium. And in Martian soil, the only conductive medium possible would be this briny water mixture, as other things such as iron oxide in the soil cannot produce enough conductivity to trigger our water sensor. Our water sensor acts as an electric probe with 2 disconnected leads. In our case, these are the lead tips of our lander nose, as they are connected to the actual like commercial probe that is part of the water sensor. And so if water exists in the soil, then it will form a connection from one lead to another and trigger a change in voltage and current in the water sensor. And a change in those two things above a certain threshold in the water sensor circuitry will trigger a current response engineered in the water sensor to go to a speaker, but that is being redirected to the communicator to the orbiter. So our results are either yes water or no water, and there is little room in between. And the detection of water here would be groundbreaking for the search for extraterrestrial life, because the existence of water in such a environment would vastly increase the odds of Martian biological life existing in an environment such as this. And this would also vastly change how we plan and prepare for such biological missions with the knowledge that biological life is much more likely than not with a detection of water. As of right now, Mars does not have any special regions, but with the detection of this, it would be likely that some special regions would have to be defined to prevent and mitigate any possibility of Earth-based biological life contamination. Yeah, sure. So I am the safety officer for Team 43, and with regards to personnel hazards and the construction of our lander, for our Earth model, it will involve using and handling lead ingots, hammers, utility knives, soldering tools, and a bit of electric circuitry. And so we need to make sure that we have safety precautions set up so that we do not injure ourselves in the process of making our lander. So with regards to lead, lead metal poses a lot of detrimental health effects. Lead is carcinogenic, and it affects reproduction and various cardiac and nervous systems. So we plan to follow the OSHA standard for handling lead, which means wearing protective clothing and eyewear when handling lead, handling it in open spaces, not consuming any food while handling lead, and washing any exposed parts of the body and hands before and after handling lead. And furthermore, handling hammers, utility knives, soldering tools, we need to make sure that we know how to handle these properly so we don't injure ourselves accidentally, which means staying focused while using these tools, and making sure that with regards to utility knives, that cuts are made away from the body. And with regards to soldering irons, avoiding touching the soldering iron when it's hot, because soldering irons can cause in extreme cases, third-degree burns. And then with regards to the environmental concerns on Mars, the fact that we are trying to find water and we are going below the surface of Martian soil in a place that is possible to contain water and also therefore Martian organisms, we need to make sure that our lander is sufficiently sterile of any Earth-based organisms that could contaminate our results. So there are guidelines set up by the NASA's Office of Planetary Protection, and our mission would categorize as a 4B mission, 4 being, I actually don't know, but the category 4B of NASA missions being category 4, that our lander is interacting with a body that contains significant interest for biological life, and then B being the subdivision for Mars, and that we are landing to investigate the possibility of Martian life. And so the guidelines set up for such a mission involve constructing this lander in an ISO class 8 clean room and sterilized using one of the 2 NASA approved sterilization modalities. And we have decided to use the vapor phase hydrogen peroxide modality because having plastic as part of our body, the alternative, the dry heat microbial reduction involving high heats would affect the structure of our lander. So we decided to use the vapor phase hydrogen peroxide, where plastic is very chemically resistant to any changes by hydrogen peroxide. And then we will also use NASA-approved biological burden assays, including the NASA standard and the LAL and ATP assays, to make sure that we do not have too much biological burden on our lander before sending it off.
Okay.
We'd like to thank the NASA Lucy mission team and the LaSpace team for facilitating this program. We feel like we have learned a generous amount of knowledge about the processes involved in developing a mission idea and going through the process of what a mission team would do with a preliminary design report. We are excited to continue the actualization. We are excited to continue the actualization of our mission plan in hopes that it will be implemented in a real life scenario in the end. Thank you.